This is called a wave demonstrator, and it's a set of magic wands with a cable running through the middle of them. What's cool is if we give one of the wands a wiggle, we get motion that gets carried through all of the other wands. What makes this a wave is that while each wand is moving and it's transmitting energy to the next wand, no individual wand travels. It's just the energy that travels. So investigating that is an interesting thing. What's the secret? It has to do with the wire that connects each of the wands. When I move one, that wire twists. And that twisting wire then puts a force, actually a torque, a rotational force, on the wands next to it. That's what's essential for waves to travel. There has to be a way to couple the motion of one of the moving objects to the motion of all the adjacent ones. This video is going to be about how that happens. In this video, we're going to be concerned about how waves travel through various instruments. And we're going to be concerned about something called frequency, how often the wave oscillates back and forth. It turns out that for almost every musical instrument and anything you could hear vibrating like a guitar or a piano or ringing like a bell, that there are some frequencies where large waves develop and seem to stand still in the instrument. And these different frequencies are what give instruments their different notes. So we're going to see that a low-pitched note has one frequency, a high-pitched note has a different frequency, and the geometry of the thing that's vibrating really determines what pitch you hear. Resonance happens in things other than musical instruments too, but it's easiest to see in musical instruments. So what we're going to do is we're going to start by playing with a spring, which shows the waves very clearly. Then we're going to transition into talking about musical instruments. And then hopefully you'll have a pretty good idea about resonance in general. So let's go and take a look at a spring. I wanted to show you guys some things about this demonstration spring that'll help us understand waves a little. The first is that when wave pulses reflect off a boundary, they change which side of the spring they're on. So I'm going to give some pulses which will be to the left side of the spring, and I want you to watch which side they hit back on from that table leg. I don't know how well you can see that, but they're going in on the left and coming out on the right. So they flipped 180 degrees. So I had these two people start with wave pulses in the same side of the spring. And notice that the waves travel towards each other. Since these are both pulling the spring up in this case, we expect that when they overlap, the spring is going to experience a pull significantly up. We call that conductive interference. What's interesting about the wave pulses, though, is then they pass on through each other as if they never met each other, and they continue on their way. If we had our two people put wave pulses on opposite sides of the spring, when they meet, the piece of the spring where they're meeting is going to experience a pull upward from one wave pulse and a pull downward from the other. And when they occupy the same space and time, they're going to cancel each other out, and that'll be destructive interference. And then afterwards, they go on their way again. So what becomes interesting is when you have a wave pulse that's got part heading in one direction, part heading above, and when that hits a boundary and gets reflected. These are in opposite directions, but as we reflect, the first part of the wave inverts while the second part of the wave is still traveling towards the wall. And the wave actually constructively interferes with itself. Let's take a look at what that looks like both in real time and then in slow motion. I'm going to send two wave pulses, one to the left, one to the right. We'll see what happens then. What's really interesting is if you get the wavelength and frequency exactly right for a wave and the spring you're using, such that the front part of the wave is big enough to take up the whole spring, and so is the back part. And you send such a wave on this spring, and when it reflects off of the boundary, it'll reflect back on itself and constructively interfere with itself and essentially move the whole medium. What we'll see here then as you keep putting in successive waves is you'll see the spring just move up and down with a huge amplitude because of the constructive interference. It's not going to appear to travel anywhere, and we call that a standing wave. We call this phenomenon resonance. It doesn't just have to happen where you get one big bump. If I sent in these two wave pulses and they're exactly matched right to the spring, the first one would reflect back on the second one and we get this. And we would expect to get a standing wave that had large amplitude here and here. Let's see what this looks like in real life. And what you get is, for certain frequencies, you get a large amount of constructive interference when the peak of one part of a wave reinforces the valley of the next part after it flips back. And what you get are called natural frequencies. Frequencies, the number of times back and forth per second, that allow huge waves to actually develop. So let's see if we can find some natural frequencies for this particular setup. So I'm going to look for when I get large reinforcing, and this is definitely one of them. So I've got one big bump. This is called the fundamental or first harmonic. If I go faster, eventually I should find one where I get two bumps. This is called the second harmonic. If I go faster, I should find other frequencies. So 1, 2, 3, I think I have 4 here. If I go even faster, I should be able to find others, where the waves essentially stay in place. But I have one briefly there. So when you're playing a guitar, and you pluck a string, it turns out it vibrates at a whole mixture of these, whatever the natural frequencies are for that guitar string. As guitar strings can teach us, the length of the string is important, and so is the tension of the string. When you're vibrating an object at its natural frequency, it's pretty easy to tell. Not only do you get a standing wave, but each wave you put in reinforces the wave that's already there. So as your hand moves up and down at a natural frequency, it's almost like the thing is moving with you. There's almost no resistance. If I pick just random frequencies, I'm really having to push and pull the whole thing. But when I find a natural frequency, it's like I'm in sync. Here's one with 3 antinodes, 3 places where it's moving a lot. If I go faster, I'll find others. Here's one. This is 5. So as you saw there, I had to go at exactly the right frequency for that length of spring and for that tension in order to get this type of standing wave to get resonance. We're going to take a look at a lab that can be done that helps you find what some of the rules are for finding these frequencies. So we're going to look for waves like the ones I just made with 1, 2, 3, 4, and 5 bumps in them. And we should have some definitions about the variables we're going to measure in this lab. First of all, we call the ends of the string or spring that don't move nodes. And we call the bumps, the place where there's a lot of motions, antinodes. So we're really looking at the number of antinodes in the string. So the other variable we're going to be measuring is the frequency. And that describes how often I wiggled my hand back and forth. In other words, a number of events per second. Sometimes you'll hear people call it waves per second or cycles per second. But at the end of the day, the unit is inverse seconds per seconds. And just to make that easier to say, we named that unit the hertz. So whenever we're measuring how often something happens, how many times per second, we can describe it in hertz. This is a lab put together by the CPO company, and it's meant to show how a guitar string vibrates. We have an elastic cord, which is fixed at a fret on top, and then it's plucked by this thing called a wiggler, which basically wiggles it back and forth. And it can do this at any frequency we want. We have this control panel here, And we can see that right now it's doing 8.6 back and forth per second. Not much is really happening with the string. No big motion. And that means that waves knocking off the fret and coming back, they're not interacting constructively with the waves coming from the wiggler, so we don't see any big motion. But we saw from our springs yesterday that there are certain frequencies where we do expect to see waves overlapping with previous waves. It'll be interesting to see if we can find which ones those are. So I'm just going to go up until I see a large standing wave. And there it appears to be. Get a little better than that. So we're fixed at either end, which we have to be, because that's where we're holding the string. We've got a lot of motion here in the middle, as the waves going in bounce off and overlap with the new waves. So this has what's called a node, no motion at either end, and an antinode, a bump in the middle. And it is at 12.8 hertz. And we go up to the next interesting one. And there it is. So we've got 2 antinodes or bumps and 3 nodes. It's fixed here. It's actually stopped dead there. I can even see the dust on the string. And it stopped there. So this is 25.7. We'll keep going until we can see 3. And I think we got it right there. 1 antinode, 2 antinode, 3. 1, 2, 3, 4 nodes. And this is at 38.4 hertz. So I think you can see a pattern. At least I hope you can. If we call this the fundamental, about 13. That's about 26. So I think it's pretty obvious that that's twice the fundamental. So it appears for waves on a string, if a certain frequency is allowed, multiples of that frequency are also allowed. This one looks a lot like 3. So just to check our pattern, we'll keep going up. So the next one I expect to be like 39 plus 13, or around 52. Sure enough, there we are. 1, 2, 3, 4 antinodes. 1, 2, 3, 4, 5 nodes at 51.7 hertz, which is 4 F. And we'll do one last check. So 13 more should be around 65. And what we're seeing is that all of these for waves on a string appear to be allowed. We're close. Maybe a little too much. There we go. So 1, 2, 3, 4, 5. And 64.5. So all of this is because of the only requirement a guitar string puts on its waves that they be fixed at either end. We'll see different instruments put other requirements and have different allowed frequencies. So in our wave on a string lab, we saw that the geometry of the string, which on a guitar is held fixed at the bridge and at the fret, determines what waves are possible. Any wave that's got no motion in those two places is okay. these large standing waves only exist for certain frequencies because you need to be sending them in at the exact right frequency that when they reflect off the boundaries, they overlap themselves and build up. You need to have that kind of constructive interference. So we've gone through the patterns of that. Essentially, the lowest frequency wave that fits in, the one bump wave, the fundamental. On a guitar string, multiples of that are all allowed too. And a real guitar string, if you pluck it, it's going to play all those notes at once. And that's why there's that nice rich sound. So when you pluck a guitar string, it plays all the allowed frequencies, or a lot of them. And if you played any of those frequencies, you would notice the guitar strings start to vibrate. That's how a sitar works. It has some strings that you don't pluck. They vibrate in response to the ones you do pluck. So this isn't just true for guitar strings. Any device that works by striking, plucking, or blowing on it, and a noise comes out of it, basically has the same thing. There's some sort of natural frequency, there's some wave that develops in the unique geometry, and what waves can go are limited by what the geometry is. So one of the most famous examples of this are these devices, which are called tuning forks. When you ding an object, you send that wave out. And if there's another object that has the same natural frequency, it will start vibrating. So if I grab the one I hit to stop it, you're still hearing the note because that one's playing. So what's going on here? I'm hitting this one. It's vibrating at its own natural frequency, which is 256 hertz. That wave is going out and making the other one vibrate because it had the same natural frequency. So this is how you can actually break a wine glass with sound. If you find out an object's natural frequency, you can play that note really loud, and that should break it.
So what we're going to try to figure out now is why different instruments play different notes. We're going to look at stringed instruments like guitars or pianos. We're going to look at organ pipes that are open on one end or open on both ends. And we're going to qualitatively look at things like tuning forks and xylophones and recorders. At the end of the day, what happens is we have to look at the geometry of the thing that's resonating and where it requires nodes to be. So let's take a look at these different instruments.
So I've taken two of the tuning forks, a small one and a large one, and I'm going to let you hear the notes they play. The larger one, if I give it a whack, plays that note. And the smaller one, that note. So the smaller one is higher pitched. They have numbers stamped on them. The larger one is 293.67 hertz. And we saw that was a low note. And the higher note was 493.88 hertz.
The geometry of tuning forks is complicated, but generally the larger they are, the lower the note, the smaller they are, the higher the note. You can also change the thickness of them. This geometry is really nice because it only allows typically one frequency, or barely one frequency, when you strike them, so they're really good for tuning a single note. Most of the resonators we'll look at in this class vibrate at a number of different frequencies all at once, specifically guitar strings and organ pipes. We'll take a look at them in just a bit and we'll figure out why they allow more than one frequency. Before we do that, though, I want to take a look at one other instrument, a xylophone.
In the case of a xylophone, we just have different size blocks of metal that each have their own natural frequency.
With a piano, there's at least 3 ways to change the natural frequency of the strings. The first is we change the diameter, so you can see that as I move to higher notes, the diameter of the string gets less. You can change the tension, so we could tighten or loosen them with these pegs here. And you can change the length. This is hard to see just from looking at the top of it, but you can see it a little bit. And down below there's quite a difference. the lower notes are typically a lot longer than the higher notes, if you think of the shape of a grand piano.
So playing a piano essentially is having the hammers hit different strings, almost like you pluck different guitar strings.
In trying to figure out why any resonator plays a certain frequency note, it helps to re-examine the wave equation. So velocity equals wavelength, that's what this Greek letter lambda is for, times frequency. Meters per second equals meters times 1 over second. So the thing that is set by the geometry of a resonator is its wavelength. If you think about a piano string that we just looked at, it's held at both ends. And that tells us that whatever's going on with the particular wave, it's got to have a node at both ends because it can't be moving there. This picture should show us what one wavelength looks like. It's two antinodes and 3 nodes. Think of this as like a sine wave where each part is buzzing back and forth. So we're going to first look at the geometry that's allowed for strings and what frequency strings can play. And then we're going to look at it for open and closed organ pipes. Notice that things like tension and thickness are not part of this equation. They affect velocity. The wavelength is the thing that can't change for any resonator because of its geometry. But by adding tension or by changing the thickness, that's going to change the speed of the wave, and therefore it'll affect the frequency, the notes that we hear.
So here's a guitar string or a piano string, and as you can see, the only geometry requirement is that you have a node at both ends, because that's where the string is held. So a variety of waves can fit on there, and when you play either instrument, you get a variety of waves. That's why the tone sounds rich. The fundamental frequency, the lowest one that will fit, if you think of a full wavelength as being like a sine wave where each is bulging back and forth, this would correspond to half a wave. So basically from here to here. So half a wave is the longest wavelength that will fit on a string. Then to find the frequency of that, you solve for wavelength and plug into the wave equation. And then you find what's called the first harmonic or fundamental frequency. But other waves called the overtones, or the second harmonic, third harmonic, fourth harmonic, also fit on here because, again, all you need is a node at both ends. And so if you go through the math, and you should do this independently, you can see that 2 times the fundamental should be allowed, 3 times the fundamental should be allowed, 4 times the fundamental should be allowed. Let's look at some other instruments that aren't strings and have different geometry requirements, not necessarily nodes at both ends. In the case of a woodwind, we change the length of a pipe, and that allows air to resonate in different size cavities, giving different notes.
There's as much art and engineering in building instruments as there is science. And the techniques for making instruments that sound beautiful have been developed over many years with lots of smart people trying to figure out how to make instruments sound the best. Even this Dollar Tree plastic recorder is beyond what we're going to be able to study for wind instruments in this class. We're going to focus on 2 very specific types of wind instruments, namely organ pipes, whose frequencies they can play change depending on the length. And we're going to look at ones that are open at both ends and closed at one end. We'll start with ones that are closed at one end. So here's an extremely elegant organ pipe that I got out of the vending machine. But this shows us the geometry for an organ pipe that's closed at one end and open at the other. This made a note by me blowing over the lip of the bottle. So there's movement there. So that means there must be an antinote at one end. There's no movement here on the surface of the Pepsi, so that must be a node. So if you think about what waves are allowed to fit in there, 1/4 wavelength, the yellow one, so like this much of a wave is cool. Half a wavelength is not allowed because half a wavelength would have a note at both ends. So we don't expect the frequency corresponding to that for this bottle to resonate at that. But 3/4 allowed, that's this brown wave. So that would get you like up to here. A full wavelength, 4/4 not allowed. But then another quarter wavelength on top of this would be cool. So there's less frequencies allowed for an organ pipe that's closed at one end. So only a quarter wavelength, 3/4 of a wavelength, 5/4 of a wavelength, only these odd multiples of a quarter wavelength work when you need to have a note at one end and an antinote at the other. So plugging those into the wave equation, you're left with only the odd multiples of the fundamental, the lowest natural frequency, end up playing for this type of pipe. In the case of an organ pipe that's open at both ends, you actually have to have an antinode at both ends because air will be moving in both places. So you actually have half a wavelength fitting in the pipe when you're using the longest possible wave. It's just a strange half wavelength. It's like the middle 2/4. But if you go through and check all the waves that could fit in there, you could have a half wavelength, you could have a full wavelength, you could have 3/2 of a wavelength. So at the end of the day, when you plug into the wave equation, you get back to what you have for wave on a string. You could have your lowest frequency, and everything else that's allowed is going to be a multiple of it. So here's, I think, the most important things to remember about the last few minutes of this video, which I know got technical. For both a pipe open at both ends and a wave on a string, you get the lowest frequency, which we call the fundamental, and you get every multiple of it as being allowed. For a pipe that's closed at one end, you only get the odd multiples. And to figure that out, draw a picture. A string has to have a note at both ends, an open pipe has an antinode at both ends, a closed pipe has one of each.